Hi, good morning. I'd like to thank the International Space Development Conference for allowing me to discuss today our topic entitled Helium-3 Mining. Is this the tip of the spear for a lunar economy to supply eco-friendly fusion and quantum computing on Earth? The singular focus of our company, Lunar Helium-3 Mining, is to extract helium-3 from the surface of the moon for Earth-based existing things such as cryogenics, neutron detection, and future nuclear fusion reactors, and future quantum computing. My background's a little eclectic. I bring up the main part in green and yellow, which is the part of my background that has to do with science. In particular, I learned about helium-3 while studying planetary geology at ASU. I then went on to understand further in detail the mining aspects of helium-3 in space engineering through degrees at University of Arizona in engineering mining and in University of Colorado in Boulder on aerospace engineering. The agenda this morning will be fairly action-packed. We're going to talk about why we're going back to the moon, sourcing helium-3, why do you even care about helium-3, revenue projections if we were to go to the moon to mine helium-3, a couple of the challenges of extracting helium-3, and then at the end, some discussion about our company, Lunar Helium-3 Mining. Fundamental question is, why are we going back to the moon? We mainly go to the moon and other areas of space as a cost center for scientific research. In this case, to go to the South Pole initially to look for water and rocks and other types of minerals. For global competition, many would argue that we're in a race with China to go to the moon and potentially to prepare to go to Mars. Those objectives require continuous funding, and I would argue or have people be aware that the chances of funding ongoing onto the surface of the moon may be difficult with the present state of our economy. Just like with Apollo. There were supposed to be 20 Apollo missions and there turned out to be just 6 due to budget cuts. However, the good news is I believe there is a revenue generator, not a cost center, by going to the moon to extract helium-3, as we will discuss today, that could stand alone on its own. Helium-3 is an isotope of helium with 2 protons and 1 neutron. It's non-radioactive, it's sort of a stable gas, but the most important thing is it's got really cool, critical, special uses on Earth, which we'll be discussing today. Helium-3 comes on Earth as a decay product of tritium from nuclear weapons production. We have a very small supply in the United States and it's dwindling. It's an estimated less than 10 kilograms of helium-3 in all of the United States as an estimate. It really comes from the sun, travels with the solar wind. On Earth, it's captured by our atmosphere, so it's virtually impossible to extract it from the ground. On the moon, there's no atmosphere, so helium-3 has been baked into the lunar regolith over billions of years. There's an estimated 1 million tons of helium-3, and that's a wild estimate. It could be as low as a couple hundred tons to 2 million. The numbers are wildly different from one to the other. However, the take-home message there is there's a lot of it there. And it's in a concentration of 1 to 15 parts per billion as an estimate. We're going to discuss the concentration part later on in this discussion. There's different hypotheses on how helium-3 is retained in the lunar regolith. The regolith, again, is the soil of the moon. One hypothesis is that it's found between the grains of regolith because it travels in the solar wind, therefore it's mainly at the surface as it cannot penetrate deeper. Second, it could be bound or attached to minerals, such as what China found when they brought back a sample. They found a mineral that they've termed changstein that has helium-3 attached to part of the mineral. That could have come from bombardment from meteorites in which pressure and temperature sort of fused helium-3 into the mineral or attached it to the mineral. Also, there's been people who have discussed the affinity between helium-3 and certain minerals, such as ilmenite, that was found on some of the Apollo samples. I would caution people that the data on this is somewhat iffy at the present moment. Ultimately, all three of these types of hypotheses, and maybe more, may tell the story of how helium-3 is on the surface of the Earth. We would argue that most of the helium-3 is probably closer to the surface due to the fact that the moon, from a meteorite point of view, has been fairly quiet over the past couple of billion years. Let's discuss some present uses of helium-3. There are existing use cases of helium-3. The most important most likely would be radiation detection at borders or border security. Look towards the right in this table, and the second from the right column entitled Estimated Helium-3 in 2008. Back in 2008, rough numbers are that we used about 10 kilograms of helium-3. That was mostly for border detection. As the supply has dwindled, the use of helium-3 over the past couple of years per year is going down dramatically. Basically, what it's saying is we're running out of supply of helium-3 even for these very small use cases of helium-3. Now we're going to jump into future use cases of helium-3. There'll be two. The first one is nuclear fusion. If you look at this slide, it's kind of fun. There's a bunch of electric vehicles here, and the question is, are these vehicles green? And the ultimate answer depends on where the electricity comes from. So let's talk about that on the next slide, but I want to point out to the top right as we begin to discuss nuclear fusion, not nuclear fission. Many people think that nuclear fusion coming up is green energy. Watch the next couple slides to see whether that's true or not. So take-home message here is, your electric vehicle, is it green or not? Well, the answer right now is the bulk of the world's electricity is produced from fossil fuel burning or nuclear fission, both with significant problems. Fossil fuel has major global warming effects with up to an estimated CO2 production. If you took CO2 in a gaseous form and put it into an Olympic-sized swimming pool, it would fill about 10 million Olympic-sized swimming pools. It's going up in our atmosphere per year. Second, who would have ever thought that nuclear fission would have radioactive waste that has to be stored for 100,000 years estimate? In fact, the United States has never put this in a central storage facility. There was work on this, but it's never been completed. So the bulk of radioactive waste is stored near or at the nuclear fission centers where they produce the power. The future source of electricity, many people believe, will be nuclear fusion, not to be confused with nuclear fission. Fusion is a reaction in which two or more atomic nuclei combine or fuse under extreme temperatures to release lighter particles, and the most important thing is more energy comes out than goes in. This has taken decades to achieve, and it's finally happened. There are two major types of reactions to discuss. The first one is the reaction between deuterium, which is fairly easy to be able to be produced, and tritium. The key thing here, it produces helium-4, a neutron in energy. We call this fusion 1.0. We've coined this term. If you actually had helium-3 for nuclear fusion, you would use deuterium helium-3. You would get helium-4, a proton, more energy, and we call this nuclear fusion 2.0. The good news about fusion in general is they cannot explode, which is a big deal compared to nuclear fission. There should be no more Chernobyl explosions, for example. Nuclear fusion 1.0, the beginning of it is right around the corner with some early contracts. It's probably 10 or 20 years to really get up to mass production. Ultimately, nuclear fusion will probably replace fission and fossil fuels. This is an important slide because we've discussed tritium, fusion 1.0, and helium-3, fusion 2.0. Here is a head-to-head comparison. No one has yet figured out truly how to scale tritium for nuclear fusion yet. Nuclear fusion with helium does not require long-term byproduct storage, where it does still for tritium. The proton that comes out of a helium-3 reaction is more stable or less damaging than the neutron that comes out from tritium. So there should be less damage to reactors in humans, and it should be safer to run a nuclear fusion reactor with helium-3. Ultimately, nuclear fusion with helium-3 should be the world's first true green scalable energy. It cannot explode, there's no byproducts, and it's relatively safe. Therefore, in the distant future, in the next 10 or 20 years, it may be very possible to have very small scale nuclear fusion reactors that could power small cities, small towns, and potentially even a company or even a vehicle. With respect to development, on the left-hand side, there's been billions of dollars by many companies and many countries to work on nuclear fusion 1.0 with tritium. Only one company, to my knowledge, is actually looking at helium-3, and that's sort of a boutique company. On the right-hand side, the development of lunar helium-3 mining is in its infancy compared to the development of fusion. And one of our jobs is to let the fusion industry know that it is possible to obtain helium-3 from the moon. So how would they keep that in mind as they develop their fusion reactions for the future? From a broad stroke numbers point of view, if the whole world adopted fusion and the fuel source was helium-3, first off, fusion in general is estimated to be a $40 trillion valuation as it replaces the burning of fossil fuels and nuclear fission. If you actually, again, fueled fusion 2.0 with helium-3, you would need ultimately about 570 metric tons of helium-3 per year. That's extremely small amount of bulk compared to coal. If we actually use coal to run electricity or to fuel the production of electricity across the globe, that would be about 90 billion tons of 31 billion metric tons of coal being needed per year. So instead of billions of tons of metric coal, we're looking at about 570 metric tons of helium-3 needed to supply the reactors to produce electricity across the globe. Second use case of helium-3 is going to be quantum computing. This is a little bit more of a strategic issue and less volume of helium-3 needed. Quantum computing is still experimental but advancing rapidly. Here's one of my favorite examples of the speed of a quantum computer. Now these are rough numbers, but if you look at a 2048-bit integer and you want to factorize it or break it down into its prime components, it could take a classical computer thousands of years, and a quantum computer theoretically could do this in less than one day. The applications are staggering, from good things such as cryptography and drug discovery and maybe reduction in cancer, curing of cancer. Politically, the country that has quantum computing may have a major geopolitical strategic dominance over another. Well, what does this have to do with helium-3? You need helium-3 to cool the quantum computers down to their workable level of 0.01 Kelvin. Without helium-3, this cannot be done, and they are attempting workaround solutions. So if you can't cool it down, the error rate is pretty substantial. By the numbers, each quantum computer roughly needs about 1 to 10 liters of liquid helium-3 for cooling. Some of it evaporates every year. There's no strong estimate of how many quantum computers might be in existence. Our company has put this number together just as a reference. So if we estimated 10,000 quantum computers in 15 years, you would need about 4 metric tons of helium-3 to power 10,000 computers or to cool them down. Let's look at revenue, because that's really going to tie into the potential of going all the way to the moon, which is very expensive. Today's helium-3 prices are about $30,000 a gram, or about $30 billion a metric ton. In the early stages with quantum computing and other uses, this price may go up. As things stable down to produce electricity through fusion, the price may come down. I'm giving you today's market prices. With today's market prices for fusion 2.0, and if you again used 570 metric tons per year, the numbers are staggering in the trillions at about $17 trillion. For quantum computing to to fuel or cool the 10,000 quantum computers we talked about, you need about 4 metric tons at a smaller number, but still staggering at $100 billion. Now let's talk about some technology or issues with the extraction of helium-3 from the surface of the moon. First off, from a competitive landscape point of view, we're very early in this, but it's rapidly progressing. China has actually outward come out and said they plan on going to the moon to extract helium-3, and they intend to do it, and they've announced this. India, which is farther behind in their space development program, has also expressed an interest. The United States has no public position. Our company has been out talking to multiple different conferences, policy conferences, fusion, space, climate, and others in our small attempt to try to get the public and the government interested in helium-3. There are other private companies looking at this in the United States. Our company has a unique approach. We are attempting to work with the moon's environment and not against it. In other words, to mine helium-3 using lunar techniques, not Earth-based techniques. We will talk about this. Some of those two things that we will discuss include efficiency of mining and durability of equipment. This is probably the most important slide in this presentation. The only way there will be a positive return on investment, which is what I would consider a financial success, is that these three things come together. Without these three things, it won't work. On the bottom left, we need fusion to switch over to helium-3 as fusion comes on board, because that's the big driver of the volume of helium-3 off the surface of the moon. Second, we need a reduction in cost of transportation. We saw a significant cost of transportation reduction by going into low Earth orbit over the past 20-30 years, and we should be able to see also proportional reduction in transportation to the surface of the moon. In the bottom right, which we're going to spend some time on, is again the emphasis. You cannot go to the moon and use Earth-based techniques to mine this particular environment. Here's a slide of a mine in Australia. That's a gold mine. It has nothing to do with the moon in many respects. However, this is how mining is done across the globe. There is energy used to extract ore out of the ground. Sometimes there's blasting, sometimes there's grinding, or a combination. That ore is then taken and transported, and where it's processed, typically made smaller, and then it's heated or chemically treated to extract a precious resource, in this case gold. And what you stick out the back of the process is you throw away something called tailings, which is the wasted rock. That's a fair amount of energy to extract resource, and that's the typical process used for gold, titanium, lithium, you name it. That's basically kind of how mining is done. You've got to use energy to extract your resource out of the ground. This slide and the last slide don't look the same, but this slide shows a potential lunar mining process. It's no one particular company. This is just a graphic that we came up with. But the last slide I showed you, the gold mine in Australia, and this is very similar. There is a bucket wheel in the front, that little grinder thing, that is used to grind the regolith, because you can't blast the moon. There's no atmosphere. So you can grind it, but there's a fair amount of energy in grinding. It goes on a conveyor belt, it goes inside, and whatever this resource is either heated or chemically treated. You extract your resource, and then you dump out the back end tailings. So this process is very similar to what you saw before. There's a fair amount of energy involved and a lot of moving parts. So keep those two thoughts in mind: energy and moving parts. Okay, we're going to cover a couple of challenges, not anywhere near all of them, just a couple that we have to discuss in our limited time here today. The first one has to do with the concentration of helium-3 that we mentioned before. The good news is there's an estimated 1 million tons, which could fuel fusion for hundreds of years. The sort of bad news is its concentration is about 1 to 15 parts per billion, and the only reason we know this is basically from samples from Apollo, the Apollo missions. If you compare that to an Earth copper mine at about 0.5 part per 100, there's a significant difference in concentration. If you used a standard Earth-based mining process, we believe it won't work because the energy to extract roughly 1 part per usable, or 1 part of helium-3, you would need to dump out the back end of your system about 999 million parts of unusable tailings. The energy cost makes this process, we believe, difficult if not impractical. We have come up with a low energy extraction process designed for lunar conditions. The next challenge is the dust itself of the regolith. If you look to the top right, that's a 10 micron shot of what lunar dust looks like. Since there's never been water or wind to erode it and break it down, it's sharp and spickly, more than likely looks like volcanic ash that would come out of a fresh volcano. It's high in silica, it's charged from the solar radiation or solar wind, and it's magnetized from some iron that's either in it or attached to it. So unlike Earth-based dust, the bottom line is it's abrasive and extremely clingy. The Apollo astronauts saw this, and NASA saw this 50 years ago. And Gene Cernan said something like this: I think we can overcome other physiologic, physical, and mechanical problems except the dust. From 50 years ago, the Apollo astronauts warned us about the dust, but over the past 50 years, we have not decided we were going to go back to the moon. There's been discussions about going into deep space and Mars. So now, at least in the United States, NASA is looking to go back to the moon, and we need to solve the dust issue, or we're just not going to be able to function there. Another slide about the dust is kind of a cool or scary example of some of the Apollo missions, in particular Apollo 17. This was the last Apollo mission on the surface of the moon in 1972. There was a total of 3 EVAs, so just 22 hours of astronauts walk around the surface, and in just 22 hours, look at the damage it did to the system. One of the more scary things is it eroded 3 layers of Harrison Schmidt's boot. That's about roughly 25% of his boot, rough numbers, in just 22 hours. It adhered to virtually everything. If you look closely at the image of the astronaut there, which is Harrison Schmidt, you can see dust everywhere. It's going to damage equipment. So our solution is to attempt the mining process the least amount of moving parts. Next, the mining process, we believe, is going to require us to minimize helium-3 escaping from underneath the rover or underneath the extraction system. So in order to do that, we're going to have some thermal skirts around our rover to sort of partially contain the gas from the extraction process, and so it doesn't go shooting off into space. And in order to do that, these thermal skirts, we want to minimize their disruption, so we want to minimize, when we can, loose rocks from going underneath them. Therefore, we came up with the idea of putting a plow in front of our rover. Now, it's not going to take care of everything, but the more we can move out of the way, the better. If we used a regular plow like a snow plow, it would shove the rocks into the next up-and-coming lane as you go up and down like a field. So we came up with a bi-directional plow that I'll show you a little bit better on the next slide. This is a better schematic, excuse me, of the bi-directional plow. If you look from numbers 1, 2, and 3 in that order, in the front is a bi-directional plow that should push loose rocks, not all of them, but loose rocks around the sides of the rover. Panels labeled number 2 would contain them from going off laterally or to the left and right. And then number 3 panels direct the rocks behind the rover. So we're trying to move the rocks around and then behind the rover so it doesn't go underneath the rover and it doesn't go into the next upcoming field. I just gave you 3 small examples of how adaptation must take place on the surface of the moon. There is significantly more than that. When we created our company, Lunar Helium-3 Mining, or LH3M, we decided to take our team and say, okay, we need to ultimately work with the moon, embrace its environment, and not against it. Our team is diverse. Here's some examples of some of our teammates. And it evolves or results in collaborative innovation. It's fairly flat in many respects. It's not that vertical. This way our team members can collaborate because no one person is going to understand everything about the moon, potentially forever. But the more you can understand by collaborating with different disciplines, the better off you're going to be. Our company has, as of this presentation, 10 issued patents and many more pending. And as I mentioned at the beginning, our singular focus is on efficiently extracting lunar helium-3 and economically returning it to Earth. We do this by trying to understand the environment. We've got a diverse team that follows systems engineering and first principles. We use agile management. And the main thing here is we are focused on the 5 steps you see there, from targeting the surface to ultimately heating, directing, separating gases, and reducing helium-3 down to a liquid form for transportation. We've begun working on advancing our TRL, or technical readiness level, and we are in discussions with strategic partners. Let's sort of bring this home from the initial slide in which we said that helium-3 could be the tip of the spear for lunar economy. So again, the core objective is helium-3 mining to power Earth's future green energy and computer systems would drive the need for sustainable lunar presence. That's the main reason to be on the surface of the moon, and you need an infrastructure for that. The infrastructure is going to have to be extensive, involving multiple companies, potentially multiple countries, and that infrastructure will have to include transportation, equipment, personnel, and again, strategic partnerships. And let's summarize on this slide, and then the next slide. There is a rough estimated 1 million tons of helium-3. There's enough to power fusion for hundreds of years. The main use cases for helium-3 would be for fusion 2.0 with helium and deuterium to create scalable, true green energy. You need about 570 metric tons. That's revenue in the trillions of dollars per year. Quantum computing is the next big thing. That would be a strategic issue. You need less for quantum computing, but you still have significant revenue. As I mentioned, the most important slide in this presentation was the success triangle, which requires the reduction in transportation costs, the commercialization of fusion, and the recognition that fusion 1.0 would replace or be replaced by helium-3. And also in red, to emphasize the point, is the use of lunar-based mining techniques, not Earth-based techniques. Our company is singularly and only focused on extraction of helium-3. We do this by trying to understand the environment. We're again using a systems agile management approach. And our goal right now is to advance our wide TRL or broad TRL and build strategic partnerships. Ultimately, the tip of the sphere for lunar economy, we believe, is only helium-3, and we need infrastructure and partnership to support this massive endeavor. I want to thank you for your time today, and I look forward for questions. Feel free to email me at csalvino@lh3m.com, csalvino@lunarhelium3.com. Thank you.